on behalf of Space Education and Research Foundation, and on my personal behalf, I welcome Dr. Ritesh Kumar Mishra, the speaker for this webinar, and also all the participants who are taking part in this webinar. Today is the fourth talk of this series, and this in fact is a continuation of the question, cardinal questions that are there for solar system, and today's discussion will be mainly on the homogeneity, whether it's homogeneous or not to be homogeneous in 26 aluminum. That will be the main topic of discussion today. And as I mentioned, I think yesterday, that all the presentation, the PPT and the video are being uploaded on the website. They are available for you and all others to use as and when you like. Before I hand over the mic or request Dr. Ritesh Kumar to speak to you, I will briefly make few remarks about him. Dr. Ritesh Kumar Mishra had a very excellent academic career during school days and also his college and university days. He did his PhD at Physical Research Laboratory, where he did very excellent work, and after that he had been doing postdoctoral research work at several very renowned centers around the world in Germany, France and US. He, besides having a very good knowledge about the subject that he is dealing with, he also takes equally good interest in reading, writing and discussions on various topics of general interest. With these few words, now I request Dr. Ritesh Kumar Mishra to start his talk, and I, along with all of you, will continue listening him in the background. Dr. Ritesh Kumar Mishra, please.
Good morning and welcome everyone. Thank you, Dr. Vats, for your kind words and giving me an opportunity to share my understanding and discuss these issues with several people around. So I hope in the first 2-3 talks I've been able to convey why we are interested in this kind of an exercise or trying to address the grand question of the origin and evolution of the solar system. So in the last talk we addressed the first cardinal question, or one of the prime questions that we want to know about solar system, and that was about whether the triggered collapse or the collapse of our molecular cloud was triggered or a natural one. And from the evidence, from the records that we see in meteorites, we can very safely assume that a nearby cloud, a nearby star, during its last phase or during its death led to a triggered collapse of solar system, which have implications on how fast these bodies would form, and therefore would be able to retain a lot of heat, which will lead to melting and differentiation of these planets, thereby creating conditions, thereby trapping that much of heat, and thereby having a greater possibility of having a living planet which would recycle its energy and resources and would retain the source of energy within its core or within its bounds to be able to create a atmosphere, a magnetic field, a recycling or a cycling of several things which would be a more conducive environment for development of life in the later stages under the favorable conditions. So we saw how we tagged these events to the time scale. We'll again go through an example of one of those today. The topic for discussion today is to be or not to be homogeneous in 26 aluminium. We want to know whether the solar system started with a homogeneous composition. If it started with a homogeneous composition, how the diversity was created in all these objects. And if it did not start with the diverse composition, then it has a different implication. So homogeneity is also very important from the point of view of measuring time. Because we can measure time, we can assign something to a place, to a region, only if the entire solar system is homogeneous at certain point of time. So if we want to ascribe a particular property, let's say decomposition, and the solar system starts with an inhomogeneous composition, then we can't say which portion was mixing with which portion to give what portion of that, to give that particular characteristics of the solar system. For example, let's say we are able to trace, let's say we are able to sample the inner core of the Jupiter, which is a rocky body. So if the solar system initially starts itself with a heterogeneous environment, then the core of Jupiter has got no relation to the core of our Earth or to the composition of our Earth. But if we start with a homogeneous composition, then, and it is only later on by some process that the heterogeneity is created, then we can tag the formation of core of Jupiter to a given time to the terrestrial surface that we currently see. And therefore homogeneity, establishing the time at which the homogeneity is achieved and the way it is achieved, is very, very important to be able to understand the question of formation of solar system. So that will be the topic of discussion today. So we'll be discussing 3 cardinal questions. One of those we discussed yesterday, whether the collapse is triggered or not. Today we'll discuss this question of homo or heterogeneity in the early solar system and how that is reflected in the isotopic properties of different objects that we see. So the prime question that we want to understand today is this one. And in the subsequent talk, in the next talk, and the last of the final talk tomorrow, we'll see whether the sun was very active during its early solar system. So in summary, this is the summary slide of what we are going to conclude at the end. We are going to look at the records of 26 aluminium, which decays to 26 magnesium inside the first forming solids, which are called calcium aluminium rich inclusions. By studying the records of 26 aluminium, decay of 26 aluminium into 26 magnesium, we are going to see, or we are going to find that there is a probabilistic distribution of 26 aluminium in different kinds of CIs, and we will be able to show that each of these epochs, which correspond to major phases of formation of these objects or reprocessing of these objects, is correlated with the pre-main sequence stage of evolution of our sun. So our sun, during its pre-main sequence stage, which is characterized as class 1, denoted here as C1, class 2, which is denoted as C2 and C3. So during each of these phases, sun has a different characteristics in terms of how much of matter it is ejecting, how much of radiation it is emanating, what kind of processes are going on at that point of time into the protoplanetary disk. So we'll see that these properties of the sun is reflected in the very minuscule solids that we are going to analyze. So some of the solids of a few centimeter and millimeter that we are going to look in the subsequent slide. These will record these events, and therefore we can go back in time 4.6 billion years ago to address the state of sun on a time scale of a few 10,000 to 100,000 years. So this is what we will try to attempt today. So yesterday, if you remember, during the classification of meteorites, I said that meteorites can be classified into different types, and one of those characteristics was the three isotopic composition of the meteorites. Then at the same time, I also showed that those meteorites also tend to contain nucleosynthetic heterogeneity in 50 titanium, 54 chromium, which are the neutron-rich isotopes produced during a supernova. So what we saw that each of the meteorites has a very specific signature of 3 oxygen isotopes of delta 17, amount of 50 titanium, and also 54 chromium. There are other properties too, but these are 2-3 main diagnostic isotopic signature of large objects like Earth, planet, and they can be distinguished by this simple by the value of these numbers. So that means all of these objects are not same in the amount of refractory inclusions that was included. So we saw that initially in the last talk we saw that a meteorite consists of refractory inclusions like CIs, chondrules, and matrix, and they have a very different chemical as well as isotopic properties that we will see today. And therefore, if we make an assortment, if we randomly mix all these 3 components in different proportions, then obviously we expect that the sum total of these assorted constituents into different proportions should give us a different signature. So, but on and all, at some point of a time, that should have come from a. So we want to know at what time that starts to happen. So the first slide shows the large diversity that we see in the first forming solids. So the first forming solids display such a wide range of isotopic properties, which is 1,000 or 10,000 times more than the diversity that we see in a very large bodies like Mars and Earth. So although Mars, Earth, and Jupiter are different in isotopic composition, they are a 1,000 or even less proportionately smaller anomaly than the kinds of anomaly that we see in the very minuscule solids that are forming very early in the solar system. So one of those objects is called FUN, which is fractionated and unexplained nuclear effects. So these are CIs. Both of these are CIs, but for some reason these are highly fractionated. These are highly fractionated in isotopes like silicon, oxygen, magnesium, and therefore they speak of the extreme events, extreme temperature processes that were taking place early in the solar system. So they show a very, very large, as you can see, very large and a very distinct isotopic signature in 50 titanium. So they have a value which is 46 per mil, which is about 5% different than the values that you see in chondrules or in Earth. Similarly, for 48 calcium, the oxygen isotopic composition that for Earth is about 0. For these objects, they show a range of about -24 to -3 per mil, which is about 2.5% different, enriched in oxygen 16 compared to what we see on Earth and Mars. So these are some of the these are the objects that form within the first 2-3 million years, but they show a very large range going all the way up to 270 per mil to 0. So which means there is a very large range that is displayed by these objects. So there are objects like, these are refractory objects called platy-hibonite crystals, or in short they are called as plaques. They're hibonites, which is calcium aluminum oxide. Then we have spinel, which are shibs, which are made up of spinel and hibonite. Spinel and hibonite, they're contracted together to give a shortened name called shibs. Then we have blue aggregates, which are comprising of corundum and hibonite. Hibonite looks blue when you look through the telescope, and when you look through the microscope, petrographic microscope, and therefore they are called They have an aggregating structure, and therefore they are called blue-green aggregates. So going from these fun or CIs, which form right at the time, we can tag to the formation we can tag as the time of the formation of the solar system to chondrules, which are forming within 2 to 5 million years afterwards. These display a very wide diversity, and we want to understand how this diversity is reflected in the bodies that we see currently. So again, these diversities can be tracked through studying isotopes in these objects, and obviously, as I said in a previous talk, that each of these isotopes have a very distinct signature of where it comes from and what kind of sources can produce them. And then we can use the times of these radionuclides to tag those events with respect to the time of formation of the solar system. So in this slide, we see the short-lived, now extinct radionuclides and their half-lives. So we have short-lived radionuclides which have as short half-life as about 2 months, 53 days, to as large as 146 samarium, which have got half-life of 103 million years. The numbers for if there are no symbols beyond the edges, they all are in million years. So we have 41 calcium, which has 0.1 million year, which is about 100,000 years, to 146 samarium, which is about 103 million years. In the previous talk, I also said that there are specific nuclides, for example, 60 iron, which is produced specifically by supernova, and therefore it can be used to trace the source that produces it. The one that we'll be talking today is 26 aluminium. We are choosing 26 aluminium because 26 aluminium is one of the dominant constituents of the early forming solids. It is a refractory element, therefore the first forming objects incorporated. It has a suitable half-life time, which is 0.7 million years, which means it can keep track of its 6 half-lives. So you can track records the first 5 and 6 million years, which are the time interval of interest to us. So any larger and the larger the half-life is, the smaller resolution in time it gives, and therefore therefore 26 aluminum is a very suitable nuclide because of its abundance as well as its half-life to be able to track the kinds of processes that we are trying to understand. So 26 aluminum is a radioactive nuclide, and therefore it would decay to its daughter isotope with its characteristic half-life following a radioactive decay law. So 26 aluminum would decay to 26 magnesium in 0.72 million years. So if you look at an object and try to measure 26 magnesium in it today, the 26 magnesium in it today would be equal to 26 magnesium that was present initially, plus the radiogenic 26 magnesium that came from decay of 26 aluminum. Now this can be converted into a linear equation by dividing this equation by a stable isotope of 20 of magnesium, which doesn't have a radiogenic precursor. So we can divide it by 24 magnesium, which is the most abundant isotope of magnesium. So then we get a linear equation of type 26 magnesium by 24 magnesium measured or today is equal to 26 magnesium by 24 magnesium initial, because 24 magnesium hasn't changed, plus this 26 reflects 27 aluminum, therefore we can change this 26 magnesium by 26 aluminum because it has decayed completely. We can multiply and divide by 27 aluminum to get 26 aluminum by 27 aluminum and 27 aluminum by 24 magnesium. So if you measure in different phases or same phases having different ratio of 27 aluminum by 24 magnesium and plot it against 26 magnesium by 24 magnesium, in favorable cases we can get a line in which the slope of the line would give us the 26 aluminum by 27 aluminum at the time of its formation, and the intercept on y-axis would give us the starting 26 magnesium by 24 magnesium at the time of the formation of these objects. Because these deviations are very small, they are expressed with reference to a reference material in parts per thousand. So these are the standard values of 26 by 24 and 25 by 24. Sometimes due to a physical or a chemical process, both the isotopes can be simultaneously fractionated either in the environment itself or because of the measurement conditions. And therefore, for a very robust measurement, we consider these mass fractionation issues. We correct for these mass fractionation issues by this kind of a mass fractionation correction law. So we get 26 magnesium is equal to 20 delta 26 magnesium minus beta times of delta 25 magnesium. So a mass fractionation corrected delta 26 magnesium, which is a reflection of this same, can be plotted against this, and we can get a line which would give us the value of 26 aluminum by 27 aluminum at that point of time. So if you are somehow using some of the state-of-the-art machine that are currently available, we can go down, we can derive, we can measure each of these phases very accurately, and in an object which hasn't had an isotopic disturbance because of their pristine character and the other characteristics, then we can the error on this isochron, which is shown by the two adjoining red lines, can be as low as 30,000 years, and therefore the events at these time scales can be tracked or inferred. So we can track events happening 4.6 billion years ago at a time scale of 34,000 years or of the similar magnitude. So again, this is something that I said yesterday again, but it is important to reiterate it again. So if let's say aluminum magnesium was homogeneously distributed in the solar system, then because of a physical, chemical, or any other process, if that aluminum magnesium is redistributed in different objects, and those objects come together to form a solid, then because they have incorporated different 26 aluminum, which would have come as the aluminum into those phases, then because they have a differential amount of 26 aluminum by 26 aluminum, the one having larger 26 aluminum would decay into to give larger amount of 26 magnesium, and therefore if we measure today, we would get a line like this, where the slope of this line would give us 26 aluminum by 27 aluminum at the time of its formation. However, if that process doesn't happen at time t equals to 0 and it happens slightly later, then the fractionation would again, the same process happens again over here at this time. Then we would get a line with a shallower slope but a higher intercept. So we can, if we can precisely measure both the intercept as well as the slope, then we can, then in a homogeneous environment, this kind of a trend of having a higher slope and lower intercept, or alternatively a lower slope and higher intercept, should always exist. And this principle will be used to ascertain homogeneity in the early solar system object. So a brief word about meteorites for those who did not, who were not present yesterday. A brief introduction one more time. So meteorites. This is an image of a chondritic meteorite. This is a sliced, polished section of that meteorite, in which you can see there are several spherical blobs and blebs, which are called chondrules. Then there are inclusions, which are primarily made up of refractory material, and therefore they are called as refractory inclusions. And all this is cemented together by a dust and powder of a few microns in size. That is called matrix. Typically, a meteorite is named at the place where it falls. If it is find from from a desert, then typically a number indicating the year it was found and the sample number that it was collected is given. So this is, for example, this is an Antarctic meteorite that was found in the Queen Hills region. It was collected in year 1999, and it was the sample number one. It was sample number 177 that was collected during that expedition. These letters and numbers indicate their group or their clan. So this is a carbonaceous chondrite of Renazo type, belonging to a petrographic tribe 3.0, where 3.0 is the most pristine meteorite that have not seen any alteration either due to liquids or due to melting or heating it. Expectedly, if you mix something with water or if you heat it, the original properties of those objects because of the interaction with heat or water would change, and that is not the interest that we have currently. So we are looking to find meteorites which have got very pristine character. Although we have a lot of meteorites, unfortunately we have very few meteorites which have got such kind of a pristine character. And that is also expected because we are looking at something which formed 4.6 billion years ago, now having had its life and journey through the interplanetary medium for such a long time. So how do they look like in an enlarged image? So this is the same object in an enlarged image. So these objects pop out very clearly in a X-ray map, and you can clearly see that the calcium aluminum rich inclusions can be very easily traced out by the combined X-ray map of the object so this is a combined mosaic of magnesium, calcium, and aluminum, where the abundance of magnesium is shown in red, abundance of calcium is shown in green, and abundance of aluminum is shown in blue. So an object that is rich in calcium and aluminum would appear greenish blue, bluish green. So these objects are CIs, or calcium aluminum rich inclusions, shortened into CIs. Chondrules, which are primarily made up of olivine and pyroxene, are rich in magnesium, and therefore they appear as red. Metals, which are iron and nickel, they are seems to be absent over here because this is a map of magnesium, calcium, and aluminum, and we are going to study the CIs in this particular object. So let's say a few words about CIs. So calcium aluminum rich inclusions, they are, as I showed in the previous picture, they are irregular shaped objects. They could be up to a few centimeters in size, and their abundance varies in different quantitative groups. The abundance can be as high. Their abundance can be as high as about 12% in carbonaceous chondrites, but they are relatively rare in other kinds of chondrites. They are primarily composed of oxides and silicates of calcium, aluminum, titanium, and magnesium, from which they derive their name. And based on their primary mineralogy, which is phenol, melilite, anorthite, and phosphite, they're classified into different types, A, B, and C, or a phosphite type, depending upon the differential abundance of these minerals, which constitute these CIs. A typical type A, type B, or fine-grained spinel rich is shown over here. This is a backscattered image of meteorites taken from Ifimoka, Vicano, and Vigrano. The scales are also indicated. This is about 500 micron. This is about 100 micron, and over here, this much would be about 1,000 micron. So if you look at these CIs in their elemental map, expectedly now you can see you can very easily clearly differentiate these CIs. So type A CI are primarily made up of aluminum-rich melilite, and therefore this is comparatively cleanest of these all. They are made up of melilite, and type B are melted. So they also consist of anorthite, shown as blue labs over here, pyroxene pyroxene which are grayish blue somewhere over here, and the spinels which are appearing as magenta color over here. Then we have type C, which are again slightly rich in magnesium compared to A and B. And we also have very small objects in like nodules which are formed. So again, you can look at different scales. This is 10 micron, this is 200 micron over here. This much would make 500 micron. On this entire scale is 3 centimeters. So this is a very large object, which is rarely found or which is primarily found in CV type of content. So if we plot them on this kind of a ternary plot, where one apex is denoted by corundum, the other apex is denoted by larnite, and third apex is denoted by forsterite, then A, B, and C would lie in different region on this plot, expectedly because of their different mineralogical compositions. If a solar gas of if a gas of solar composition were to condense minerals out of it on cooling, then the red line indicated then the red line shows the order in which different minerals would condense out of it. So we would have corundum first, and then corundum would go on to interact with more of calcium oxide to form ebonite, then gehminite or the aluminum-rich melilite would form, and then melilite would go on to, to anorthite pyroxene, and then finally it would go on to forsterite, which is what we see in chondrules and aluminum-rich chondrules over here. So A, B, C, aluminum-rich chondrules over here and chondrules over here. If the bulk composition of our Earth were to be plotted, this is where it would plot. So the objective of carrying out such a study, apart from understanding homogeneity and heterogeneity, is also to be able to distinguish at what time these different CIs form. So as you can see, those CIs look very, very different, and we need to know how these different objects form, and thereby we can infer the conditions under which they form. So by studying these CIs, we can also find out whether there is a relationship that is followed between these seemingly different objects. And if there is a relationship between the other dominant component, which is a chondrule. So is there a genetic relationship? Is there a genealogy between CIs and chondrules? Then we can figure out how this heterogeneity is transferred between these objects, and therefore we can form a relation as to how these objects form and how the transportation or a transformation of a material from one object to the other takes place. By studying the mineral phases in them, we can fix the environment in which these are forming, and therefore again constrain the cosmochemical conditions, the variation in cosmochemical conditions with time. One of the major interests is also to be able to understand whether why do these differences exist? Why doesn't the same, if the process is the same, what creates those different conditions for these objects to be formed? Is there any correlation between the way the sun is evolving and the characteristics and properties that exist in these objects? So to be able to do that, we studied CIs and aluminum-rich chondrules, which are the first forming solids of the solar system. Here is a typical example of a type A CI from Mifimovka. The inset box is shown over here, and you can see that the phases over here, spinel is about 15-20 microns. There are refractory minerals like perovskite, which is calcium titanium oxide, hosted inside the spinels, and then these are all surrounded by millilite, surrounded by pyroxene. So a spinel perovskite is over here, which is spinel which is made up of magnesium and aluminum would appear as magenta or as pink. Calcium titanium would appear somewhere over here, and then it is surrounded by melilite, which is surrounded by pyroxene. This is the same order in which, if you remember in the earlier figure that I said, this is the order in which minerals would condense. So this is type A CIs are shortened. So these microscopic objects are recording the sequential order in which different phases condense and form. So we are going to study something at these micron scale, and the attempt is to carry out a very high precision studies of these phases to be able to make analytical measurements which are very precise, to be able to get those precisions on the isotone, to be able to make the inference that we are interested in knowing about the early solar system. So some of the other objects are shown. Again, they show the same nodular character. You have a nodule of spinel inside, surrounded by a melilite, surrounded by a diapside, and then a phosphatite all around it. So as you can see, again, these are 10 and 20 microns. So these are the 10 and 20 microns, and as you can see, most of them are not very rich in aluminium, not very rich in aluminium that we are currently interested in to look for, because we are trying to look for excess of 20 excess of decay of 26 aluminum into 26 So some of the other objects of different types, because we expect them to form at later point of time, and if we want to precisely measure, if we want to precisely say that heterogeneity exists, we should be able to measure different objects of pristine kind forming at different objects to be able to infer that kind of a thing. So type C, post-right bearing, other kind of amoeboid olivine aggregate, they always studied. The minerals have been identified in them. So the green appears as a melilite. Spinel is indicated by this pink color in all these. The phosphorite is which is magnesium silicon oxide is shown as the red color. So about 12 to 13 of these objects were measured. Uh, these are Since they are the very precise measurements were required for this kind of a study. They are carried out only at a few places, and it requires a high amount of sophistication in not just in analytical analysis, but in the stability of instrument too. Because, for example, even a very small variation in temperature by, let's say, a few degrees would generate so much of a noise on the measuring device, typically a Faraday cup, that that uh, that a variation in temperature by 1 degree would generate a noise to a level which would correspond to a point of 20,000 to 40,000 on a Faraday cup, which would mar all the effort that we have taken to make those precise measurements. So we have to worry about each of these factors like um, stability of the ion beam, stability of magnetic sector, to be able to make that kind of a precise measurement. So, which is a rather difficult job, but it is not of an interest to be talk over here. So we will skip that to come to this slide. I showed this slide earlier as an example that somehow if you are able to hold on to 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 manage the experimental conditions and find those kinds of phases which have suitable ratios, suitable compositions, and yet here pristine enough, then you can analyze several of them within a CI like this. If you plot them on this line, then and if you have done a good job, then probably you might be able to get a precision to a level of 34,000 in the kind in this kind of a CI, and therefore be able to be able to date these objects to this level of precision. So this CI has found 0.1 million year after the beginning of solar system, and the precision on this kind of a measurement is at the level. So in this 100,000 years after the formation of the solar system, the precision is measurement is 1/3 of the time that this corresponds to. We'll see the significance of it in the following slide. So about 12 such objects, some mostly consisting of CIs and some FOBs, and some aluminum-rich chondrule were analyzed. Because this is an aluminum-rich chondrule, it has a much steeper, much shallower slope. So the value was 10 to the power minus 5 over here. In this, the value is 2.1 times 10 to the power minus 6. The intercept is also very, very precise, which is 0.249 times 0.249 per mil. So this is a summary slide showing all those objects that were analyzed by analyzing different objects forming at different times. So objects like type A, type B, type C, CIs, AOAs, and fine-grained mineral-rich objects, and then aluminum-rich chondrules. So we analyzed a large diversity of objects forming at different point of time with the best precision that could be possible. So we could achieve a we could find their 26 aluminum by 27 aluminum from their precise isotones. Expectedly, for them, we found that their intercept, which has been represented by delta 26 magnesium I0 or I initial with a star. So these were also very, very precisely measured to the second decimal in at the per mil level. In these from their mineral composition, we could derive what is their bulk 27 by 24 magnesium. So we could take a map of the entire object and calculate the abundance and the bulk abundance of that object. We also found out their bulk 25 magnesium from the measurement itself. We'll see how these are helpful. Because the following slides are going to be slightly technical in nature, so we'll just go over what I said at the very beginning. I said in the beginning itself that if the process that fractionates aluminum and magnesium between the object at time t equals to 0, then it would have a steeper slope and a lower intercept on y-axis, where the slope would indicate the amount of 26 aluminum by 27 aluminum it had at the time of the formation. However, if the object forms at a later point of time by more or less a similar kind of a process or a different process itself, that doesn't matter, then it would have a shallower slope but an expectedly higher intercept in a homogeneous scenario. So we are going to use this principle to be able to test for projecting. So let's say the process which fractionated the element is governed at a different times. So if the fractionation happens at, let's say, time t equals to 0, that established its bulk 27 aluminum by 24 magnesium. If that happens at a different point of time, then the isochrone that we would have very, very different intercept. So if that process happened at time t equals to 0, such that its 27 aluminum by 24 magnesium is equal to 5, then we will find that the isochrone will have an intercept on y-axis corresponding to about 0.6 per mil. However, if that event happens at the last minute itself, then it would only have an intercept like 0.2 per mil. So let's say we measure an object which have got 26 aluminum by 27 aluminum measured today is equal to 3.58 times 10 to the power minus 5, such that it has a bulk 27 aluminum by 24 magnesium equals to 5, and delta and magnesium loss which would correspond to 60%. So that means after 60% loss of magnesium, so if we lose 60% of magnesium to give the value 5 today, so we have a value 5 today, it would have started with a value 2 at some point of time. So there could be 3 possible scenarios: that it happened right at time t equals to 0 over here, that the evaporation took place so that it attained this number, or the formation of the object took place right at this point, and then it evolved continuously till the complete cycle. Or it could have happened 200,000 years later on at this point of a time. If it happened at this point of a time, the object would have initially evolved with this along this line. And therefore, if we measure today, we would only see the intercept of the line at this value. However, if the object formed right over here, or the evaporation happened right over here, then this is the value that we see. So if we can very precisely measure the intercept as well as the slope, we can also tag at what time that process happened, and thereby infer several things about the event and processes. So that is the intent of showing us very simple diagram. Now, if you plot all the objects that we have analyzed and draw their back trace their evolution lines, we can see that all of them converge somewhere over here, which means all these objects can be derived from a composition which would have a composition something like this, which is similar to the composition that was previously reported for the bulk CIs. Right? So if the solar system would have been heterogeneous, then these lines are under no constraint to go to this particular region. They could have come over here. This line could have come over here. This line could have come over here. It's only in a homogeneous scenario that the precursors of it continue to record, and they all can be derived from this particular composition. And thereby we are able to establish that this should be the starting composition, which is able to explain not only the diversity in these objects, but also that the precursors were created somewhere over here. And then subsequently at different times, these objects were forming or were melted to give the kinds of objects that we see now. So we have analyzed different types: A, B, and C, fine-grained ones, aluminum-rich chondrules, and this kind of an inference can be drawn from this particular diagram. So aluminum magnesium can be inferred. The canonical value 5.25 corresponds to time t equals to 0, and therefore we can infer the time at which these events would have happened. So this is a plot which shows, so we have two distinct reservoirs. One makes up the chondrule, which is, chondrules are rich in magnesium but poor in 26 aluminum. The other reservoir is CI, which is rich in aluminum but poor in magnesium. So if we retrace the path they would have taken from a homogeneous environment, then we find that this is the best composition that can explain both the CI as well as the chondrule. The earth line is also indicated in this diagram by the golden or the yellow line. So precursor of earth that we see currently now somewhere over here also passes through this region. So a homogeneous reservoir with this composition simultaneously explains the isotopic property of CI and chondrules, which are forming at two different times. These are forming at time almost at time t equals to 0. These objects are forming one starting from, let's say, 1 to 5 million years later on, yet they are able to trace, and thereby we are able to establish that the solar system should have an initial composition of 5.62 times 10 to the power minus 5, and the initial magnesium isotopic composition should be equal to minus 0.052 plus minus 0.13 per mil. This is a much precise value than what was previously known. or previously derived from the bulk CIs. So you can see the bulk CIs initially could constrain the value from about 0.002 to 0.067. From that level, we have now been able to constrain it to this level, which is a very significant improvement. Now, how do we relate them to the stellar time? As to how is there a correlation between what we see in the diversity of these objects to what we see, what is happening into the nascent sun or the early sun that is happening. So, observations have been made of young stars in our neighborhood. In five in the five nearby molecular cloud, and evolution of star and the time period, the median time period of different stars in different stages have been shown in this figure. So we have found that the median lifetimes of the star in its pre-stellar stage is about 0.5 million years. In the class 0 stage, sun-like star spends about 0.1 million years. In class 1 stage, it spends about 0.44 million years. In flat stage, it spends 0.35, and in class 2, it spends about 1.5 million years. So these are the typical median lifetimes of sun-like stars, during which it evolves through these phases, which has come from the astronomical observations of several young stars in our neighborhood. In our neighborhood, during each of these stages, class 0, 1, 2, and 3, star has a very different property in terms of how much matter is flowing out, what is the size, what is the accretion rate, and therefore these processes determine what kind of temperature and pressure exists at that particular point of time. For example, if you see during this time, during these times, there is a generation of outflows. So during class 0 and class 1, because of a larger accretion of matter at the rate of 10 to the power minus 4 to 10 to the power minus 5 solar masses, such a large high accretion rate leads to generation of to biflows and jets, which means if you can create a solid over here, then they also have a mechanism to be transported outside, which gets much weakened at the later stages. So you can't make an object over here. You can make an object over here, and then there exists a mechanism which will transport it out. But if you make an object over here, then there is a less likelihood for it to be transported outside, because there are no strong jets or outflows which are driving it to a farther off distance. Similarly, if you look at the X-rays or the energy during different times, we see that it is very strong during these times and these times. So the X-rays are strong, therefore it is generating a lot of heat, and therefore the objects would suffer, would see different thermal events during these times. Also, you can note that during this time, this is adiabatic, and during these time, these are convective and radiative. So during this time, temperature would continue to rise because of the process itself, and therefore they could again be reflected into the objects that form at that particular point of time. So what we have done in this one is to draw a probability distribution of the 26 aluminum that we see in these objects. So what is the probability given these sets of objects that we will see these values? So we analyzed about 12 CIs in our studies, and we had about 8 or 10 CIs previously. Our curve, so we could by drawing a probability density function, we could infer as to what is the probability that those numbers could exist. So we see that the probability that the CI would record 5 times 10 to the 5 is pretty much higher than something like 6.25 or 3. But we see that there is a clumping at these values too. So if we combine both of them together, we get these light gray shaded area, which is a combination of the result from our and about 6-8 CIs that were analyzed previously with similar amount of precision. We require a very high amount of precision to be able to draw these probability curves. Otherwise, we would have a probability like this, and then we will not be able to discern the separate events that we are interested in. Now, if we can assign the time where the time the if we assign the homogeneous composition to the end of class 1, the composition that we derived from this plot, 5.62 times 62 times 10 to the power minus 5 and delta 26 magnesium of minus 0.052 time per mil to the end of class 0 stage. Then all the diversity that we saw in the very first slide, the large diversity that we saw in the very first slide can be explained. So such a large variation, which seemed like a 30% variation in the properties. So the high temperature character of these, the high amount of nucleosynthetic heterogeneity in these two, a very general or a low level of these in chondrules can be explained with the help of determining that composition, assigning that to the end of class 0 phase. So by this kind of a plot, we are able to understand how the diversity of CI exists, and we are also able to say that this happens because of the star evolving through different phases. It was during this phase that this star was highly adiabatic, and the mass accretion rate was very high. So very high temperature was generated because the accretion rate was high. The star was in a state of adiabatic accretion, and therefore much higher temperature was achieved. So the object that formed over here are ultra refractory compared to the objects that are forming over here. So we see most of the objects over here because this is the major phase where most of the CEIs form, and they are primarily of type P. So, but then these CIs, these events occur later on at a later point of time again, and therefore their transformation or their reformation at these events also happens. So by studying these objects, 1 type A, 2 type B, 5 type C, 4 fine-grained inclusions, 2 AOAs and 2 aluminum from the pristine meteorite frame of Gaia and Vigrano, we could establish that the 26 aluminum must have been homogeneous with seeded 26 aluminum by 27 aluminum of 5.62 times 10 to the power minus 5. Prior to that, the homogeneous composition from which all these materials can be derived is minus 0.052 plus minus 0.13, which is precise, which is much more precise than what was known previously. So homogenization doesn't happen instantaneously. This happens over a period of time. Most of the CIs form during this peak stage, which is why the probability density is high at this point of time, and that is for a very short period of 30,000 kilo years. But subsequent heating events have continued to happen, which transform or reset the isotones. They continue to happen 1.5 million years later, which is more or less also the same time the chondrule formation takes place. So then we could also relate that the properties of these CIs correspond to the pre-main sequence stage of our sun. So each epoch corresponds to the median time scale of pre-main sequence stage evolutions of the star. The class 0 phase implies homogenization of 26 aluminum and 26 magnesium, and class 1 is the major epoch of CAI formation. And with that, I will stop here and let you absorb and ask me questions that might be talking to you because of the technical nature of several involved things that I said during this talk. I acknowledge taking some view graphs and images from some sources, and I'm thankful to authors and contributors for those images. Most of this work was done with Mark Chosidon at CRP Genosi, where we have state-of-the-art machine. It's called 1280 secondary ion mass spectrometer 1280 HR2. There are only about 12-15 such machines around the world. Only 4 or 5 of them are being used for study of cosmochemistry or studying of meteorites to understand formation. I especially thank Mark Chosidon for being such a good, nice mentor and letting me explore this project with him. With this, I'll let you ask any question that you might have.